Alright, so we're going to be moving into something that's kind of cool. It's obviously, I would assume at this point you've never seen it, and it's called parametric equations. And if you look at your calculator, and we're going to get to this in just a minute, but if you go to your mode, which is this button right up here, and you hit mode, and you're going to go down, and this is something we've never changed before. It's this function tab. There are multiple ways of evaluating and studying and graphing functions. And what we're going to do in this unit is we are going to get out of the rectangular coordinate system with the standard XY plane. And we're going to start talking about the parametric coordinates. And that is actually still similar. You are on the XY plane, but it adds a new variable of time, which we'll talk about in just a second. And then we're going to go to this polar equation right here. That's what that POL means. Right now I'm going to stick with the function notation right now. And again, we will change that here in just a minute. But that's what I want to start with, is talk about what is a parametric equation, how does it relate to your regular function notation, and how, again, what we're going to be doing is just working right now and just graphing using this new type of equation. So some of the notes I have up here for you already. Parametric equations, they allow you to introduce a new variable called the parameter. And that variable is going to be called t. And this variable typically represents time. So what we're going to be able to do is not just have a graph, but be able to kind of see how that graph is traveling, or a point on that graph. How is that point traveling along the curve? So we're going to be able to kind of add time into the functions that we are already used to drawing. So again, what it looks like, again, and I have an example for you right here. So here's our example of what a parametric equation is going to look like. You can have an x and a y value in terms of t, time. So what we're going to do if we want to fill in the chart, because anytime you graph something the first time, usually the most basic way to do that is to plot points. So we're going to plot points. So I have a parametric equation for you, and we're going to plot points, and we're going to graph those points and see what it looks like, and see if you can kind of see how these x and y coordinates kind of fit the curve that we're looking at. And once we've done that, we will do something called eliminating the parameter, and you will be able to kind of convert this to a regular function notation that you're used to seeing. So here we go. If we're going to fill in this chart, we start with our t-values. Our t-values, again, represent time. So maybe like 2 seconds before the beginning of our reading, or 2 seconds after. I don't know. It's not an application at this point, but we're going to plug in these points and see what we get. So I'm going to start with our x value right here. And the x value, the first one, is going to be plug in -2. For t, it's going to be negative, oops, I should fix that. So that's going to be -2 minus 1, so -3. So that's our first x value. And then plug that into our y value, and that's going to be, that might be hard to fit in here, but I'll do my best. It's going to be 2 minus t squared. So that's going to be -2 squared. So if you work this one out, and I'm going to erase this because I'll run out of room if I don't, but this is going to be 2 minus -2 squared is 4. Notice that is 2 minus a positive 4. So we are going to get -2. So there's your first official point on your graph. And you can even go ahead and graph that point. We have -3, -2. So there's my first point right now. Okay. The next one, I'm going to plug in -1. So I'm going to have I'm plugging in right here. Okay. So I'm going to go -1 minus 1. You put parentheses if you need it. We don't really need it. But that's going to be -2. And then we're going to have 2 minus -1 squared. Just like before, it's going to be 2 minus, and then -1 squared is 1. 2 minus 1 is 1. And I can plot that point, so -2, 1. Okay, so there's your second point. Next up, we're going to go t minus 1 again. I'll plug it in with a 0 for t. So that's 0 minus 1 is -1. and then we're going to plug in for our y value, so that's going to be 2 minus 0 squared is 2. So my next point is going to be negative 1, 2. So negative 1, 2 is right there. Next up, you're going to see we're plugging in t minus 1 more time. We got 2 more times there actually to do it. So you plug in 1 for t, so it's going to be 1 minus 1 equals 0. And then we're going to go plug in our y value here. So it's going to be 2 minus 1 squared, which is 2 minus 1, which is 1. So that's going to be 0, 1 for that point. And our last one is going to be plugging in 2. So I'm going to go t minus 1 here. So I'm going to go 2 minus 1 is 1. And I'm going to do my y value. So I'm going to go 2 minus 2 squared, which is 2 minus 4, which is negative 2. So we're going to plot the point 1, negative 2. And again, hopefully you kind of see that we have what looks like a parabolic equation. You would be correct if you saw that. So when you graph it, understand that we have a restriction on our for our time here. So we are only graphing this from when the t is from negative 2 to positive 2, which is kind of like doing a domain. It tells me, you know, I start at that first point that I graphed, and I stop at the last point that I graphed. So we're not going to draw a parabola like this with arrows. We are actually graphing in between these 2 points. So that's one thing that's going to happen. That's a little different, but that's still kind of similar because you're used to graphing functions. We've talked about domains and things. But the next thing that happens is understand that this represents this parabolic curve as it travels through time. So direction matters. It's going to show the direction of this curve. So we're going to put in arrows in this graph that represent the direction that this curve is heading. So if we have any sort of projectile, this is going to tell us what direction that projectile is going. So when you graph this, obviously only limit your graph to the parameters that you're given, and also include the arrows in your graph that kind of says the direction that this graph is traveling in, and that's going to represent that time. And again, you'll see that I have that written down here. It's in the paragraph already anyway. But we are going to place arrows, as I already did, on each segment to indicate the direction the object is moving. But then if you want to kind of show what this, and this is an important thing to, if you want to graph a function or parametric equations, what we're going to do to help us get that graph is we're going to do what's called eliminating the parameter. So this is going to be a big deal here. So to eliminate the parameter you have to understand is that t value. So what we do is we're going to pick one equation, typically the x equation, and we're going to solve that equation for t. So this is eliminate. I'm going to put the note up here. So I'm going to do eliminate the parameter. Okay. So in order to do that, we are going to, again, take this equation, x equals t minus 1, and I'm going to solve that for t. And it's like solving a system of equations. You'll see what I mean here in a second. So now that I have that t value solved, I'm going to take this second equation, which is solved for y, and we're going to plug in this x plus 1 value in for t. And it's like, again, in algebra when we would solve a system of equations by substitution. What this is going to do is get this equation in terms of x and y, which is what we're used to dealing with. So this won't include the time aspect, but we can see the actual structure of the graph this way. So this is going to be y equals 2 minus x plus 1 quantity squared. And if I wanted to rearrange it, I would just go ahead and make this negative x plus 1 quantity squared plus 2. And now it's in vertex form. So you can see this graph. My hk value is going to be negative 1 comma 2. You can see that's where the vertex is. You can trust me that all the other points work. Obviously it's negative, it's opening down. We have all those components. And that's eliminating the parameter. There's a couple ways of eliminating the parameter. which will is going to be kind of the next focus of what we're doing. But one thing that's going to bleed into our next lesson that I'm going to introduce to you now is how to graph this on your calculator. You see you have the calculator up here. I want you to get used to using it, and we're going to do it. We're going to do it right here. So if we want to graph this, what we're going to first do, and I am, just so you know, I have the notes already here for you. So and again, the thing I want to state, I've already stated. Again, the graph, if I actually graph this on the calculator, it's going to be the entire parabola. If I restrict it, I can restrict the domain, but it's not going to necessarily show the direction. So anyway, if we're going to graph this exactly what I have right here, I'm going to get this graph on our calculator in parametric mode. We're going to have to take our calculator, go to the mode, and we're going to go down here and we're going to change this to parametric. So go on down, highlight parametric, hit enter, and then go to your y equals screen. And you're going to see on your y equals screen we have that x1 and y1. So these are all, notice, are going to be in terms of t. That's x1t and y1t. So we're going to plug in those equations that we were given up above. So it's going to be t minus 1. And to get the t value, we're going to hit this variable button. Because we are now in parametric mode, that variable button is going to be a t. You'll see that it shows up automatically. So we're going to go t minus 1 for x1, and we're going to go 2 minus t squared for y1. So this is going to give us our graph, but before we graph it, just like we normally have to do anyway, we need to set up our window. So our t min, if you remember our t min, if you look at our t chart here, we're going to go from -2. Our t max is going to go to +2, and you'll see that it's traveling 1 unit at a time. So that our t step is going to represent how far we're kind of going there. Actually, that's not what t step represents. I'm sorry, we already have that scale. It just kind of fills in all the points itself. The t step is going to represent how fast this graph is going to travel. So the smaller you make this number, the slower the graph will get drawn. I'm going to show you 0.05 so you can see it slowly drawing, which is important if we there are some ones that we'll have to do here that actually represents like spirals or circles and things like that, and you want to kind of know what direction it's going, and this is what's going to help you see that. So anyway, that's that piece, and then the x min, again, as we're graphing it, we know this is going to go from, looks like 1 to -3 to 1. So I'll go -3 to +1, and I'll go by ones, that's fine. My y min looks like it goes down to -2 and goes up to +2. So I'm going to go -2 and +2. So that's my y min and y max. And then we should be able to graph this, and it should show up just fine. So there's our graph. You can kind of see how the direction it was drawing it also. And again, if you go to your window, you can make that t step, and again, I can go down. You can see all your scales here. Oops. Sorry about that. So anyway, if you want to get your t steps, make that a little bit slower. You can always go like 0.001. That might be a little slow, but it should still work. But you see how slow it's going now. And the smaller you make that number, the slower your graph is going to draw. And you also notice it will stop at those points. I could have probably made my scale bigger, but here's the thing, without having to do it again because it's so slow graphing anyway. It's stopping at this point. It's not going to go beyond that point. This is as big as it's going to get. So that way you kind of have that figured out from the very beginning. Alright, and it should have just shot there. I noticed the screen I had is way too big, so I had to fix that real quick. Okay, so the last thing we're going to really work on at this point is just basically, right now, just eliminating the parameter. We want to be able to see our graphs, get them from that parametric version that we have into that function notation that we're used to working with. So I have some examples we're going to work through, and I'm not even going to work through all of them because I already did kind of one with you. So I'm going to just go ahead and do 3, 4, and 5. And 3 is very similar to what we just did in terms of, again, eliminating the parameter. we're going to do a basic version here where we take one of the equations, and just like I did before, and I have the steps up here, we can eliminate the parameter by solving one equation for t, and that's going to usually be that x equation, and then we're going to substitute it into the other and then solve for y. So that's what we're typically going to do unless we have a trig function. So I'm going to take this one, I'm going to take that first equation, and I'm going to solve that first equation for t. So this is going to give me x equals, I'll just write it up here first, 2t squared minus 7, and I'm going to add 7 to both sides. I'm solving this for t. So I'll get x plus 7 equals 2t squared. Then I'm going to divide by 2. So now I have t squared is equal to x plus 7 divided by 2. So now that we have that, we can square root both sides. So you get t equals plus or minus the square root of x plus 7 over 2. Alright, so now that you have that solved, what we're going to do is we're going to take that t value and we're going to plug it into that second equation, which is 3t minus 1. So I'm going to have y equals 3, and I'm going to do this 2 times the square root of x plus 7 over 2. What do we have? Minus 1. So I'll start with that one, and as we solve it, I'm going to zoom in just a little bit right there. This may seem scary. I mean, it's not so bad, it's just algebra, but this is 3 halves times the square root of x plus 7 minus 1, and that is a radical function. You can solve for x and make it a parabola if you need to, but this is a radical function. This is going to, if I was graphing it without all the crazy details going on in here, I can always remove that. So if I was going to graph this, you'd see I'd be going left 7, 1, 2, 3, 4, 5, 6, 7, and I'd go down 1, and I'd have this point, and this is a graph that kind of has this curve to it. This is a square root function parent graph. So I have that graph, and then we just do the exact same thing with the 3, and then I have negative square root x plus 7 over 2 minus 1. Now instead of doing these steps again, I mean, I guess really one step anyway, I guess, but this is just going to be a negative 3 halves square root x plus 7 minus 1. And if I graph that, come up here, it's going to create this curve. You put them together, you get a sideways parabola. So again, we'll work on graphing these with our next lesson, so you kind of see you can kind of see the graph by eliminating the parameter, and that's what this one would look like if I did graph it just by plotting those points. So we can do that either way. Number 4 and 5 are going to deal with our trig function. So if we have a trig function, we're going to have to use some trig identities. So I would assume when you're looking at number 4 here, and again, I could be wrong, but I'm probably not. If you're going to find, what we're going to have to do on these is we're going to have to figure out some sort of trig identity that uses sine and cosine. And that's going to be our key, our first step to eliminating the parameter. And you'll see how that's going to work out when we do it here. But I would assume for most people that the trig identity that shoots into your mind is going to be this one. It's going to be sine squared theta plus cosine squared theta equals 1. Okay, so that's the one I'm going to use because there's no other trig functions. It's not like we have like sine over cosine is tangent. Now we got to deal with a tangent because we can't deal with that because we don't have one. So what I'm going to do is I'm going to take both of these functions. I'm going to solve each one for sine and cosine, and we're going to substitute it into that identity. So that means my first equation, this x equals 2 cos t, I'm going to go ahead and divide both sides by 2. So I know x over 2 is equal to cosine of t. The second equation, I'm going to say that is y plus 1 equals 3 sine t. And I'll divide both sides by 3, so y plus 1 equals sine t. So I have these two equations for cosine and sine, and we're going to, again, substitute these into my identity. So this guy's going to come over here for cosine, and this guy right here, this y plus 1, it's going to come, oh, you know what, I forgot something here, I need to fix that. That's y plus 1 over 3. I need to divide that by 3, don't I? So I'm going to put that 3 under there. So now I can move it over. So I'm going to move this guy over here. He's coming, he's coming, he's coming. And that's my x and my y values. So I'm going to plug in for sine squared theta. I'm going to plug in y plus 1 over 3 quantity squared. And then for my cosine, I'm going to plug in x over 2 quantity squared equals 1. If you distribute those squares, we get y plus 1 quantity squared over 3 squared, which is 9, and we get x squared over 4 equals 1. And I don't think I need to explain what this one is to you, but I'll say it anyway. This is an ellipse. Yay, ellipses! Yeah, that's where they come from. So you kind of see as you're doing these, I had a sideways parabola, which is that first one. This one is an ellipse, so we're dealing with conic sections. They appear quite a bit, as you will see. So there's my conic section, and I do have one more to go here. I do have number 5 I want to show you guys, and that's where I'll wrap up this video. So number 5, I have to write this one back down here. So I have x equals 5 tangent t, and I have y equals 2 secant t. And I want to eliminate the parameter. And when I say eliminate the parameter, basically we're trying to get that xy function. So to get this one going, we're going to have to think hard of a trig identity that uses tangent and uses secant. I'll let you think for a second. Okay, you've thought for a second. So hopefully you're coming up with what I'm coming up with, because this is the one we need. Tangent squared theta plus 1 equals secant squared theta. Now, the way I'm going to write it, and you might already see what's about to happen if you are, maybe you are, maybe you aren't, I don't know. But we're going to go ahead and subtract these. I'll set this, actually I don't want to do it that way, I'm sorry. I want it equal to 1, so I'm going to move the tangent to this side, but I'm going to write that on the left. So I'm going to go secant squared theta minus tangent squared theta equals 1. Hopefully you're starting to see where we might get a hyperbola out of this, because that's what's going to happen. So anyway, when we set this hyperbola up, we've got to look at these two functions. I'm going to start with the tangent one. So if I take that tangent equation and I solve for tangent of t, I'm going to get x over 5 equals tangent t. And the other one, I'm going to get y over 2 equals secant t. Again, we're going to substitute these values in for tangent and for secant. So this is going to become y over 2 quantity squared, and this is going to become minus x over 5 quantity squared equals 1. So we get y squared over 4 minus x squared over 25. And that is a hyperbola. It opens up and down, it's centered at 0, 0. We just dealt with that with our conic sections. So again, we have some practice problems. You'll see I have that listed for you to do in terms of practicing eliminating the parameter. So again, go ahead and give these a shot, and I'll see you guys in class later.